The Earth's mostly iron and nickel molten outer core generates an electromagnetic field extending from the north to the south pole, protecting the planet from harmful solar particle radiation. Fluctuations in Earth's magnetic field strength, caused by daily changes in solar wind and intermittent solar storms, can impact the geomagnetic field models necessary for navigation in satellites, aircraft, ships, and cars. Magnetic field models vary depending on the data collection location, whether on or near the Earth's surface, or from satellites in low Earth orbit. Past research linked model discrepancies to space weather activity levels. However, a recent analysis of 6 years of Earth and satellite magnetic field models found that these inconsistencies stem not only from geophysical events, but also from modeling errors. A research team from the University of Michigan evaluated differences between observations from the SWARM mission's low Earth orbit satellites and the 13th generation of the International Geomagnetic Reference Field, IGRF-13, the Earth's magnetic field model. They focused on differences during low to moderate geomagnetic conditions, covering 98.1% of the time between 2014 and 2020. Satellite observations collected from various locations on Earth are sensitive to magnetic field fluctuations. In contrast, Earth magnetic field models, such as IGRF-13, use observations to predict the Earth's internal magnetic field without accounting for solar storm effects. Internal magnetic field models like IGRF-13 track changes in Earth's magnetic poles, such as the North Pole's annual drift of approximately 45 kilometers north-northwest. Understanding these significant differences is crucial for satellite operations using IGRF-13 as a reference and for research on the physics of Earth's magnetosphere, ionosphere, and thermosphere. Model uncertainty was highest in the north and south polar regions, and statistical analysis revealed that the asymmetry between these regions was a significant factor driving model differences. Another concern for the navigation community is the rapid change in the polar magnetic field over the past decade. Model uncertainty was highest in the north and south polar regions, and statistical analysis revealed that the asymmetry between these regions was a significant factor driving model differences. Yining Xu, an assistant research scientist in the University of Michigan's Climate and Space Sciences and Engineering Department, and the study's lead author, stated, "We assume an almost symmetrical magnetic field between the north and south polar regions, but in reality, they are very different. The two geographic poles correspond to different geomagnetic coordinates. The North Pole aligns with approximately 84-degree magnetic latitude, MLAT, and 169-degree magnetic longitude, MLON, while the South Pole aligns with approximately 74-degree MLAT and 19-degree MLON. The polar orbit track of the SWARM satellites creates a sampling bias due to the high concentration of measurements around the geographic poles, increasing model discrepancies." Arthur F. Thurno Professor Mark Moldwin from the University of Michigan's Climate and Space Sciences and Engineering Department, and a co-author of the study, said, "Understanding that what was attributed to geophysical disturbances is actually due to the asymmetry in Earth's magnetic field will help us improve geomagnetic field models, as well as aid satellite and aviation navigation."